In today's class, we'll be talking about the 13th step, which is you need to check for the buckling of the bearing stiffener. You know that there is certain amount of bending or there is certain amount of buckling in the stiffener. Okay, so you need to find out whether this buckling is within the safest possible limits or not, right? So in order to find out that, you need to calculate the term which is called as buckling resistance, okay, which is given by the formula FQD equals to A into FCD, right? So where A is the effective area of the bearing stiffener and FCD is the design compressive force, which you will be obtaining from the IS 800 2007 code book. Now, so up to here we have discussed in the last class. So in continuation to that, how to find out the area of a bearing stiffener. So here, this diagram, I guess you must have drawn in the previous class itself. So this is the web portion, which is the horizontal one, and the vertical two ones are the bearing stiffeners. Okay, these two are the bearing stiffeners. Now you need to find out the effective area of bearing stiffeners, right? So before finding out the effective area of the bearing stiffeners, you need to know what is the outstand of the core portion. So here we have calculated in the last class that the outstand of the core portion is 168 mm, right? You should know what is this 168 mm. So 168 mm is the distance from the web portion up to extending 168 mm length. So this is the outstand length, right? 168 mm is the outstand length. Now, what is the total height of this section? This portion. The total height of this portion is 220 mm. Why it is 220 mm? Because we have found out the dimensions of the bearing stiffener as a 220 by 12 mm. So that's how the 220 has come, right? And also, this is the thickness of the stiffener, which is sometimes written as TS, or sometimes you can also write it as TQ. They both are same, which is given as 12 mm. This also we have assumed in the last class, that is 220 by 12 mm, where 220 is the width and 12 is the thickness of the stiffener, right? Along with this, you should also know couple other parameters, which are the thickness of the web. This is the thickness of the web, okay, which is 12 mm. You know this, okay. Now the thing is, you should know one most important parameter, which is 20 times of TW. Okay, so 20 times of thickness of the web. We have solved this in the previous class, right? We have been telling that 20 times the thickness of the web. So this portion, that is from edge of the bearing stiffener, you have to calculate the distance, and that distance should be ranging of 20 times the thickness of the web. Okay, you know the thickness of the web, which is 12 mm. Okay, so that will give you 240 mm. Now, by using this data, you have to find out the effective area of the bearing stiffener. Now, how do you find out the effective area of the bearing stiffener? It can be found out as, you know, you have two bearing stiffeners on either sides of the web. So I'm multiplying with 2 times of, okay, what is the length of the outstand or core outstand length? It is 168 mm. So you have 168 mm at the top, and you also have the 168 mm at the bottom. Okay, so 2 times of 168, that is the length, into the thickness of the stiffener, which is 12. Okay, so this 168 is the core outstand length, and this 12 is the thickness of the stiffener. Okay, plus area of web. So that is technically 20 times of TW. Okay, 20 times of TW into the thickness of the web, which is 12. Okay, you know that 20 times of TW value is 240 mm. So that calculation will give you 2 times of 168 into 12 plus 20 times the thickness of the web, that is thickness of the web is 12 into 12, that is again the thickness of the web. So therefore, the effective area will be 6912 mm square. So this is the effective area. Now you have to find out the FCD value. You got to know the value of area. Now you need to find out the value of FCD, which is design compressive force. So in order to find out the design compressive force value, again, the backward calculation. In order to obtain the value of FCD, you need to know the value of slenderness ratio, where slenderness ratio is given by KL by R. Now, in order to find out the value of R, you need to find, in order to find out the value of slenderness ratio, you need to find out the value of R, which is radius of gyration. That will be given by under root I by A. You know the value of area. In order to find out the value of radius of gyration, you need to know the value of moment of inertia. Right? That's how the back calculation comes. So let's first solve with the moment of inertia value. That is I equals to BD cube by 12. That's a simple formula. So where B is the width of the stiffener or the thickness of the stiffener, not width, it is the thickness of the stiffener. So that is 12. Okay, the thickness of the stiffener, you can see 12 mm into the depth D cube, right? So D is the 168, right? You have got this core outstand. So 168 plus 12 cube divided by 12. So what is this 12? This 12 is the thickness of the web. Okay, so what exactly you're doing is you're calculating the total distance from here up to here. Okay, so you have 168 here and you also have the 168 here plus the thickness of the web. So that's how 2 times of 168 plus 12 has come. Okay, then so this entire term is related to the stiffeners. Now you also have to calculate this value for the web portion. Okay, so that will be 240, which is the 20 times of TW value, into D, where D is the thickness of the web. So the thickness of the web is 12, that is 12 cube upon 12. So this entire term is related to the web portion of the I section. So if you solve this one, you will be getting the value of moment of inertia as 42.17 into 10 power 6 mm power 4. So from this, you can find out the value of R, that is root I by A. You know the value of I, that is 42.17 into 10 power 6. And you also know the value of area, which is 6912 mm square. So if you solve for this one, you will be getting it as 678.1 mm. And then you have to find out the value of KL by R. You know the value of K is taken as 0.7 times the depth of the web. Okay, KL is taken as 0.7 times the depth of the web, where K is specifically 0.7, which is fixed for the plate girders. Upon R, that will give you 0.7 times the depth of the web is 1400, which we have calculated in the very beginning steps. And the radius of gyration is 78.1, and this will give you 12.5, right? So you got to know the value of KL by R, that is slenderness ratio. Now you need to find out the value of FCD, which is design compressive force. Now, how do you find out the design compressive force value, that is FCD value? So you know plate girders, okay, plate girders belong to buckling class C. Why it is belonging to buckling class C? Because all the built up sections are belonging to buckling class C. So this we have discussed by using the table which is provided in IS 800-2007, right? So when a section is belonging to buckling class C, you have to use table 9C of IS 800-2007 in order to obtain the value of FCD. Okay, so use table 9C of IS 800-2007 and you have to calculate the value of FCD when lambda equals to 12.55. Okay, so upon doing the interpolation, you're going to get the value of FCD as 226.24 newtons per mm square. So I'm not doing the interpolation terms. We have been familiar with the interpolation concept, so I'm not going to do that again. However, so that's the final value of FCD. So what we have to find out now? We have to find out the buckling resistance, that is FQD value. So what is the final formula of FQD? That is A into FCD. You know the value of A, which is the area, and you know the value of FCD. So therefore, buckling resistance, that is FQD, equals to A into FCD, where area is 6912 into the value of FCD is 226.24. So this will give you 1563.77. 1563.77 kilonewton. And remember, whatever the buckling resistance you are getting, this must be greater than the reaction force. So the reaction force which we have calculated is 996 kilonewtons. Okay, so that must be greater than the reaction force, or you can also take it as maximum shear force. Anything is same. Okay, so since the FQD is greater than the reaction force, okay, since FQD is greater than the maximum shear force or the reaction force, that is capital V, the stiffener is safe in buckling. So the stiffener is safe in buckling. Suppose, say for example, you got the FQD value less than V or less than the shear force. What you have to do is you have to increase the dimensions of the stiffener. Okay, instead of 220 by 12, you should go for the upper values, or you should come down to the lesser values. It depends on the trial and error calculation. Okay, so fine. So that's how you're going to find out the buckling resistance of stiffener. Now let's find out the next step, which is the 14th step, which is the bearing strength of end stiffener. So you have to check for the bearing strength of end stiffener. So check for bearing strength of end stiffener. So how do you check this? So in order to check this, you have a specific formula, which is bearing strength is given by FPSD. It is not B, it should be D. So FPSD equals to AQ into Fi upon 0.8 into gamma m naught. AQ into Fi upon 0.8 into gamma m naught. This formula is not available in your code book, so you have to remember this formula. And remember, this FPSD value must be greater than the reaction force, that is capital V, which is the shear force. So let's find out whether it is greater or lesser. So in order to find out the FPSD value, you should find out the value of AQ. Okay, so how do you find out this AQ? It is the area of end stiffener. AQ represents the area of end stiffener. So you know you are providing the stiffeners at both ends of the plate girder. So I'm multiplying with 2 times of 220. What is this 220 is? 220 is the width of intermediate stiffener, width of the load carrying stiffener. We have solved it here. This one, 220. Okay, from this you are going to take the value. So 220 minus 15. So what is this 15? 15 is the coping length, which we have discussed in the third model problem. I mean, in the second model problem. That is when you are designing the plate girder using intermediate stiffness. We have said that what is this coping length, and you have to assume the coping length as 15 mm only. Don't go any other, don't assume any other value. So this will give you 4920 mm square. Okay, so therefore FPSD equals to the value of AQ is 4920 and the value of Fy is 250. upon 0.8 into gamma m naught, which is 1.1. So if you solve for this one, it will be 1397.73 kilonewtons. And you know this value must be greater than the reaction force. So the reaction force is 996 kilonewtons. So therefore, end stiffener is safe in bearing. End stiffener is safe in bearing. Again, if you get the value as FPSD is less than V, then what you have to do is, one simple thing is you have to change the dimensions of the load bearing stiffener, which you have assumed as 220. You should go for the next higher possible value, maybe 230 or 240. Okay. Now, in continuation to this, we also have to check the torsional resistance of end stiffener. Okay. So whether the end stiffener will get torsioned or not. So whether it has sufficient capacity to avoid the torsional force or not. So let's keep the heading as check for torsional resistance or restraint. It's not resistance, it is restraint provided by end stiffener. Provided by end stiffener. Now, in order to solve this one, you have to refer clause 8.7.9 of IS 800-2007, which will give you a formula that is IS, that is moment of inertia of stiffener, must be greater than or equals to 0.34 times of alpha S into D cube into TCF. Okay, so if you refer clause 8.7.9, you will get this formula, right? Now, so here you have to find out a typical term. Okay, so the first thing is you have to find out the value of alpha S. Now, how do you find out the value of alpha S? In order to find out that, you also have another formula which is given by 30 upon LLT, that is length of transverse stiffener, upon Ry whole square. This formula is there in the same clause. Okay. Now here the question is, you have to find out the value of LLT and you also have to find out the value of Ry. Okay. Now, how will you find out the value of LLT? LLT equals to, it is usually taken as whatever is the length of the stiffener, length of the girder, that one you can take directly. So how do you take that? Is a 1 times of L, that is length of girder or span of the girder. The span of the girder which is given in the question is 24 meters. So that will be 24,000 mm. So remember, this is the span of the girder. So how do you know whether it is has to be, whether the length or whether the span of the girder is multiplied with 1 or not? So if you refer page 68 and table 15 of IS 800-2007, for fully restrained, we know in the question it is given as restrained. So for fully restrained, the value of length or the span has to be multiplied with 1. Okay, that's how the LLT value has found. And now you also have to find out the value of Ry, which is radius of gyration, that is given by root I by A. So now let's find out the value of I, that is the moment of inertia. That can be found out as 2 times of thickness of the flange into width of the flange cube divided by 12 plus depth of the web into thickness of the web cube divided by 12. Okay, so you know all the values of this, that is 2 times of thickness of the flange. You have 2 flanges, one is the top flange and the other one is the bottom flange. That's why I am multiplying with 2. So the thickness of the flange is 40 and the width of the flange is 500. So 500 cube upon 12 plus depth of the web is 1400 and the thickness of the web is 12. So 12 cube upon 12, this will give you 833.53 into 10 power 6 power 4. So you have got the value of moment of inertia. Now you need to find out the value of A, that is the area value. So that will be taken as, you have two flanges, so 2 times of width of the flange into the thickness of the flange. So that will give you the area of the flange, both flanges technically, plus area of the web, that is depth of the web into thickness of the web. So this entire term is corresponding to flange area, that is AF, and this entire term is corresponding to web area, that is AW. So this will give you 56,800 square. So from this you can find out the value of R. So that is 833.53 into 10 power 6 upon 56,800. Okay, so this has to be, the value of R has to be 121.14 upon calculation, right? So with this data, you can find out the value of alpha S. So therefore, alpha S equals to 30 upon LLT by RY whole square. What is the value of LLT? It is 24,000. So LLT, that is 24,000 divided by RY, which is the radius of gyration, that is 121.14 whole square. So this will be 7.64 into 10 power minus 4. Okay, the alpha S value will be 7.64 into 10 power minus 4. Now you need to find out the value of IS, that is moment of inertia of stiffener. So that equals to, you have the formula, that is 0.34 into alpha S, that is 7.64 into 10 power minus 4 into D cube. Remember here it is not small d, it is the capital D. Capital D is the total depth of the I section. So that will be 1480 cube. Okay, so how this 1480 is coming? 1400 is the depth of the web, 40 is the thickness of the flange, and again you have the bottom flange thickness, which is again 40. So 1400 plus 80 will give you 1480 into the TCF value. Okay, so that is again 40. TCF is nothing but the thickness of the flange. Okay, this is thickness of the flange, or you can say it as TCF is nothing but thickness of compression flange. Since you have both thicknesses, both flange thicknesses are same, I'm just mentioning it as TF. So fine. So this value, if you solve, it is equating to 33.68 into 10 power 6 power 4. 33.68 into 10 power 6 power 4. Okay, so remember, this is the required value. This is the required value, right? So we have to check. Okay, we have to check whether this is within the safe limits or not. So in order to find out that one, you have to find out the moment of inertia of stiffener, the moment of inertia of stiffener at center line of web. Center line of web. So how do you find out this? So capital I, that is moment of inertia, equals to thickness of the web, that is 12, okay, into 2 times of the length of the stiffener, right? What is the dimension of the stiffener? It is 220 by 12. So from this I'm writing down, okay, plus thickness of the stiffener cube divided by 12. Okay, so if you solve for this one, you will be obtaining the value as 92.345 into 10 power 6 power 4. So as I was telling, this value 92.345 is greater than the 33.68 into 10 power 6. So the required value is 33.68. but how much you have provided is 92.34, so which is very much safe. So therefore it is safe. Okay, so that's how you're going to check the torsional restraint of the stiffener or torsional restraint of the stiffener. And the next step is you have done all the checks to the stiffener, that is load bearing stiffener and the load end bearing stiffener, and you have designed the dimensions of the webs and flanges. Now what you have to do is you have to connect all these elements, right? You have the elements now individually. Now how do you connect it? So technically you're going to design the plate girder, so obviously you're going to use the welded connection. So let's connect web and flange initially. Okay, welding of web and flange. So first let's connect flange and web. Welding of web and flange. Then once after you do this step, then we'll connect the other parts. Okay, fine. Anyways, I'll just continue this. So we are going to assume the fillet weld. Okay, you are going to assume the fillet weld on either sides. Assume fillet weld is provided. So I'll go a little faster because you know these calculations. So I'll just go with a little higher pace. Anyways, fine. So you know the shear force equation or the shear stress equation, that is QW equals to VA Y bar by 2 times of IZ. Okay, so here V is the reaction force or the maximum shear force, that is 996 kilonewtons, and A is taken as area of a flange, that is width of the flange is 500 and thickness of the flange is 40. That will give you 20,000 mm square. Okay, and the value of Y bar, right, it is calculated from the center distance to the center of the flange. That will be 700 plus 40 divided by 2. This you must know the calculation. So 720 mm. Okay, so this 700, how does it is coming? It is coming from total depth of the web divided by 2. So 1400 is the depth of the web, and then half of it will give you 700. That's how it is coming. So, and again, you also have to find out the value of moment of inertia, right? So moment of inertia of both the entire I section, that is flange and web, has to be calculated. So that is BD cube by 12, where B is the width of the flange, that is 500, and capital D is 1480 cube divided by 12 minus 500, that is the width of the flange, minus thickness of the web, that is 12. Okay, into small d cube by 12. Small d is nothing but the depth of the web, which is 1400 upon 12. So this will give you 2.35 into 10 power 4 mm power 4. So now you know all the values. You can just substitute the values in the formula of QW. So once you substitute the values, you will be obtaining as 0.305 kilonewton per mm. Okay, so this is the shear stress. I mean, by using the shear stress equation, you have got this value. Now, you need to find out the strength of weld per mm length. So let's find out that. So strength of weld per mm length. So that is given by P equals to, that is strength of the weld. I'm just mentioning it with P. So capital P equals to length of weld into throat thickness into FWD. Okay, so usually for shop welding, okay, for shop welding, okay, it is taken, I mean the FWD value is taken as 189 newtons per mm square. This is available in code book, but instead of looking at the code book, you can directly remember the value of FWD for shop welding is taken as 189 newtons per mm square. And here the weld size, okay, assume size of weld, that is S equals to 6 mm. You're just assuming this value. Okay, usually it is provided greater than 5. So I'm just taking it as 6 mm. So therefore, throat thickness equals to 0.7 times the size of the weld. So that will be 0.7 times of 6, which will give you 4.2 mm. Okay. So from this, you can find out the value of P. So therefore, capital P equals to LW, that is length of the weld, into throat thickness into FWD value. Okay. So here, what is the LW value? You're calculating it for 1 mm length. Okay, that's what I have written. Strength of the weld per 1 mm length. So length of the weld, I'm taking it as 1 mm into throat thickness is 4.2 and FWD is 189. Why 189? When you are doing shop welding, the value of FWD is 189. So that will be 0.749. Okay, 0.749 kilonewtons per mm. And remember, this value must be greater than the value of 0.305 kilonewton per mm. So this is the condition, 0.305 kilonewton per mm. So that is again the safe value. Okay. So now what is this 0.305? It is the value of shear stress equation term, that is QW. So we have found out here QW equals to 0.305. So from there I'm getting this value. So if it is safe, then you have to do one more step, which is called as center to center spacing of the length. So center to center spacing of weld length, that is given by P by QW. What is the value of P? It is 0.749 and QW is 0.305. So which will give you 2.6. Okay. Now here the effective length of weld has to be assumed as 100 mm. Assume, so these are the constant terms. So assume effective length of weld as 100 mm. So this is the constant term. Make sure you remember this value. So therefore, center to center spacing of weld, center to center spacing of weld equals to 2.6 times of 100. So 2.6 is coming from here and 100 is coming from here. So that will give you 260 mm. So therefore, clear spacing has also to be found out. That is, clear spacing equals to center to center spacing of the weld, that is 260 mm, minus effective length of the weld, that is 100 mm. Okay, center to center spacing minus effective length of the weld. Okay, which will give you 160 mm. Okay, but the thing is, the clear spacing value. Okay, so if you refer clause as per clause 10.5.5.2, what does it says is clear spacing should not be greater than 12 times the thickness. So it is usually thickness of the web. So what is the thickness of the web? 12 mm. So that is give you 144 mm. Okay. So from this condition, since 160 mm is less than 144 mm, you can provide. Okay. So since you can write it here, since 160 mm is less than 144 mm, therefore provide just a minute, provide clear spacing of 100 mm and effective length of weld as 100 mm on each side of web. Okay, now you have connected the webs and flanges. Now the other step which you have to solve is you also have to connect the stiffness with the web, that is end bearing stiffness. So connecting end stiffness with web. So you have to connect the stiffness also with web. Now here also, in order to find out this one, you have the specific formula. If you refer clause as per clause 8.7.2.6 of IS 800/2007, it will tell you that Q1 equals to TW square upon 5 times of BS. Okay, so what is BS is width of the stiffener. So TW is the thickness of the web, that is 12. So 12 square upon 5 times of width of the stiffener is 220. We know that the dimension of the stiffener is 220 by 12 mm. Right? That's how you're getting the value of 220. So which will be 0.13 kilonewtons per mm. Okay. So from this, you have to find out the value of net shear force. Okay. So the net shear force has to be found out. Before finding out the net shear force value, so let me write that formula once. So net shear force equals to Vz minus shear force resisted by web. Vz minus shear force resisted by web. What is Vz? Vz is the reaction force, that is 996 kilonewtons. Now you need to find out the shear force resisted by web. So shear force resisted by web, that is FCDW equals to B1 plus N1 into TW into FCD. So this is available in clause 8.7.3. So this formula we have been using. But here, when you have the combination of the loads, remember when you have the combination of the loads, the value of B1 is directly taken as 0. And the value of N1 is taken as total depth divided by 2. That is half of the total depth. That is total depth is 1480 upon 2. That will give you 740 mm. And the thickness of the web is 12 mm. So now you have to find out the value of FCD. In order to find out the value of FCD, you need to know KL by R value. Okay. Now let's find out that one. So how do you find out this thing? So this can be done in a very simplest possible way. So in order to find out the value of FCD, I said you have to find out the slenderness ratio, that is KL by R. Right. So here you can do some short check, that is taken as the value of K is taken as 2.43. Okay, times of the depth of the web divided by the thickness of the web. So this is the shortest possible calculation. So you can directly calculate like this, the value of KL by R. So that will be 2. Remember, this specific thing is applicable for combination of loading cases. Don't apply this technique formula for remaining 2 other cases which we have discussed. So 2.43 times of depth of the web is 1400 and thickness of the web is 12. So that will give you 283.5. So you know, right? You know, when you use table 9C of IS 800/2007, use table 9C of IS 800/2007. Right. So what you have to do is, when lambda equals to 283.5, you have to find out the value of FCD. But the thing is, for lambda value, you don't have the value of lambda, you don't have the value of FCD when lambda is greater than 250. You have the values up to 250 only. This we have discussed in the last class, right? So you should find out the value of FCD when lambda equals to 283.5. So how do you find out? You are going to do the extrapolation. Instead of doing interpolation, you have to do the extrapolation, right? So you know that one. So I don't repeat the same process again. I'll just write in a simple statement that by extrapolation. So if you don't have an idea about how to do the extrapolation, you can watch the video, which is the second part of this particular lecture. Okay, that is being uploaded to YouTube also. You can check down there. So by extrapolation, for lambda equals to 283.5, the value of FCD is obtained as 17.94 newtons per mm square. That's how you're getting this value. So therefore, FCDW equals to, what is the formula? B1 plus N1 into TW into FCD, right? So B1 value is 0 and N1 value is 740 into the thickness of the web is 12 into FCD is 17.94. So if you solve this one, it is obtained as 159.31 kilonewtons. Okay, so therefore net shear force equals to, what is the formula? Vz minus shear force resisted by web. So Vz value is the reaction force, which is 996 kilonewtons, minus shear force resisted by web is 159.31. So this value will give you 836.69 kilonewtons. That's how you're going to find out the net shear force value. Now you need to find out the length of weld. Length of weld. So that equals to total depth of web, that is small d value, that is depth of the web, which is 1400 minus 2 times of 15. What is this 15? I have been telling that it is the coping length. Okay, don't forget this one. 15 is the coping length. So this will give you 1370 mm. So this is the amount of welding has to be done. So up to 1370 mm, you have to do the welding process. And again, you have another formula. If you refer clause 8.7.2.6, you have Q2 equals to. So how do you find out this Q2 is net shear force, that is 836.69 upon the length of the weld, that is 1370. So net shear force is 836.69 and the length of the weld is 1370. So if you solve for this one, it is obtained as 0.61. Just a minute. Yeah, 0.61 kilonewtons per mm. Okay, so therefore the final value of QW equals to Q1 plus Q2. What is Q1 value? You have found out already, that is 0.13. Okay, and the Q2 value is 0.61. So which will give you 0.74 kilonewtons per mm. Okay, so therefore force on each weld size equals to half of QW. So that is 0.74 upon 2. So that will give you 0.37 kilonewtons per mm. So again, you have to find out the strength of the weld per mm length. So strength of weld per mm length. So we have been assuming the 6 mm as the size of the weld. 6 mm size of weld. So I'm not writing the same statement again here. So the strength of the weld P equals to, so you know the formula, right? That is LW into TT into FWD. LW into TT into FWD. So the value of FWD is 189 when you are doing shop welding. So, and the value of LW is taken as 1, and throat thickness is 0.7 times of S, that will give you 4.2, and FWD is 189, that is for shop welding, and this value will give you 0.794 kilonewtons per mm. And as I was telling earlier, this value must be greater than 0.37. Yeah, 0.37 kilonewtons per mm. So which is safe. Okay, so up to here you can solve, and I mean there is a couple of steps. So there are a couple of more steps also. So I'll let you know what are these. So the next proceeding steps will be calculated as center to center spacing of weld. Center to center spacing of weld, that is given by P by QW. What is P? It is 0.794 upon QW value is 0.37. That will give you 2.14. Okay, so as in the previous step, I am assuming effective length of weld. Effective length of weld equals to 100 mm. Therefore, center to center spacing of weld equals to 2.14 times of 100. That will give you 214 mm. You can approximately assume it as 200 mm or 220 mm. It's up to you. So therefore, clear spacing equals to 200 minus 100. That will give you 100 mm. So 200 is the center to center spacing of the weld, and 100 is the effective length of the weld. The same process which we have repeated. And as I was telling earlier, the clear spacing should not be greater than 12 times the thickness of the web. So the thickness of the web is 12, that is 144 mm. Okay, since 144 is less than 100, you can provide. So therefore, provide 6 mm fillet weld of 100 mm effective length and 100 mm clear spacing on each side of stiffener. Okay, so now you have found out the dimensions of the flange, you have found out the dimensions of the web, you have found out the dimensions of the load bearing stiffener, right? You have done certain amount of checks, right, for torsional web buckling, shear force in the web, flange buckling criteria, all these things you have done. And in the last step, you have done the connections, right? Again, in connections, you have two cases. One is connecting the flange and the web, and the second case is connecting the web portion with the stiffeners. Okay, this is the short case of what we have done so far. Okay, so this is the entire process of the design of a plate girder when you have the combination of loads. In the next class, we'll discuss about another model problem, which is the last model problem, that is without using any stiffeners. That means you are not going to use intermediate stiffeners, and you are also not going to use end bearing stiffeners. So how to design such kind of stiffener, that will, such kind of plate girder, that we'll discuss in the next class.